Good morning there, ladies and gents. Welcome back to another practical session. The idea of this video is to assist the students, especially how to make a measurement of the internal resistance of a circuit. Now what we've done before, we have constructed the circuit, we have measured it as part of your practicals, and we've determined that it actually works. And for the guys who don't recognize the circuit, it's the common emitter amplifier. We're going to use that as an example. But what the method is going to be applicable to any amplifier out there. So whether you want to measure a sound system, whether you want to need to do the internal resistance measurement for your hi-fi in the vehicle, in your car, where the guy's doing the boom boom and all those things, all amplifiers can be analyzed and practically measured in order to confirm whether or not it is working as such. So the circuit is this. The instruction requires us to add this, to modify our circuit. The circuit has got added to it now a variable resistor, a rheostat or a potentiometer, depending on what side of the planet you're from. And we are going to measure a voltage difference across this resistor. We will also know what is the input voltage to the amplifier, and the difference of that using Kirchhoff's law will give me what is the Rin total of that amplifier. So we simplify the whole amplifier into a single resistor. But again, like we did with AC analysis, we're not physically changing the circuit. We are adding components, yes, but the amplifier itself remains untouched. This whole circuit must be here. You cannot just pull it out and have one resistor sitting there. It will not work. So up to now the measurements has been done, and we reach step 6 of the instructions. Step 6 says, and I'm going to read it with you, it says the following: the measurement of Rin total is done indirectly, magic word, indirectly, since it's an AC resistance and cannot be measured with an ohm meter. So if I use a multimeter, putting it on ohms, I will be impossible to measure that input resistance, because it's dynamic. It's definitely not a physical resistance as such. So we know what the output voltage is from our experiments before. The output signal is measured with an oscilloscope and recorded with the amplifier operating normally, which means no clipping or no distortion. We expect a clean sine wave on the output. The rheostat or test is then inserted in series with the source circuit, and that's what we are doing here. It's putting in series. So we have the signal generator C1. After that, before we go to the base, I then install a variable resistor, and that is shown here in figure 9.3. Then we say the rheostat is then varied until the output voltage drops to 1/2 prior to that, what the output was before we included this resistor. So we're going to write down what is V out, typically in the order of about 2 volts. Then we're going to install this to the board, and we are going to adjust it until the output voltage, this V out, is not 2 volts anymore, but down to 1 volt, or whatever the voltage was that you had. I'm using 2 volts as an example, and I know in practical lab your output voltage will be different. So do not try to cheat the system and just taking what is given here on the video, because I know what we are doing in the practical lab. So we vary the variable resistor until the output voltage V out is going to be half that of the voltage that it started with. In this condition, it means V in equals the voltage across the resistor. So it means this voltage here is the same as here. So what have I made? I've made a voltage divider. And from Kirchhoff's law, if I know that this voltage equals this voltage, it means the internal resistance must equal that test voltage. So with this condition, the two voltages are the same, and that implies that the R in total from the circuit must be equal to the test resistor value. All that we then do is we remove the test resistor and we measure it using a normal ohm meter. And with that method, you can then measure the R in total and write it into the table. So let's go about. Let me show you how to do the connection. The first component that you guys are confronted with would be this little blue box. Sometimes they are black, sometimes they are white, sometimes they are upright, sometimes they are lying flat like this one. I prefer this one for the breadboard just because of the easy way that we can use it. But what it is, it's a variable resistor. If you look at the symbol, it has 1, 2, 3 legs. Don't worry about this little line sitting between this arrow and this side. Let me close it with my finger first. But 1, 2, 3 legs. If I look at the component, there's one leg in the middle, that is the arrow. There's one leg this side and one leg this side, and that is this side and this side. So in order to keep life very simple for yourself, is we're going to just simply connect it into the breadboard, and I'm using the valley as my position or the split between the top side and the bottom side. I have seen many students, because of lack of experience mostly, doing this. And what happens? This side is fine, it's going to be connecting somewhere in these 5 holes, but this line and this line is actually connecting to itself, which means there is a short circuit right through. I can prove it. Get the multimeter here, put it on ohms. It is a 10 kilo ohm resistor, and just to show you guys, there it is. And if I now do this, and I put it like this, and we measure from here to here, I get a short circuit. That's not what we're looking for, ladies and gentlemen. If you do that, this whole component means nothing, and you have not constructed the circuit that we have required you to do. So what is the best way to do it? Turn it 90 degrees. Make sure that single one, I put it usually on top, and I put the bottom 2 at the bottom. So I cross the bridge, that little valley, and now if I measure between these 2 legs, I do expect to see something very close to 10 kilo ohms. In this case 9.33, and remember, part of your measurements is to say, but we are measuring like so and such. So, and using the practical value. So this 10 kilo ohm resistor reports 9.33 ohms or kilo ohms onto my multimeter. If I now take and I touch here, you will notice 4.6, and if I move it to this side, 5.35. If I add the 2 values together, then I will still get this value, 9.33. That's how it works. So what did I do? If I measure here, it's a straight resistor. The straight resistor tells me it should be close to 10 kilo ohms, 9, whatever we had. If I move this one here, the resistance path is now going through here, through the arrow, through the little part of the resistor, not everything, returning this side. And that's why I got a smaller reading like that. And if I move it to this side, I also get the difference. So this side plus this side is the total. That's how a variable resistor works with 3 legs. To recap that idea, 9.32, if I measure it from pin, the middle pin there, 4.41 and 5.35, the addition of these 2 will be 9.4 or 9.35, which is perfect. So it works. So in this case we need some wires. The circuit requires me to disconnect C1 and move it out. So what I do is I disconnect it here and I connect it to this side. So by doing this, that's the first thing that we do. So my signal generator will be connecting here, instead of this side. So I move this one. Then this little wire here, take the middle pin and connect it to the one side of the capacitor, like so. And there you go, it's the white wire sitting here. And then we take that other side and we take it back to the base. So there it goes to the base, and that pin of the circuit connects there. Now, ladies and gentlemen, you've got a variable input that's going to do exactly what my circuit is doing. It's going to share the voltage, input voltage coming from the audio generator between the amplifier and the variable resistor. And by adjusting this, we are going to observe the output. If I change that, we observe the output until it is half of what was the full output without this component. And once we reach half, then we're going to pull out the resistor, and now we should be able to measure what is my circuit. So what side did we measure? We use this side and this side, no? And that can be anything. So I get 3,25 for this example. Not necessarily the correct answer, I'm just using it in order to confuse you, but to show you the method. So if I do that, that is the method. And now this resistance must equal the resistance internally to the amplifier, or in total, and because the two voltages are now shared equally. Well done if you can do it, and come and impress us in the lab. Thank you very much.